It's Asher Yahalom's turn to give us a seminar. We should say Happy New Year to Asher because he's just been away for a couple of weeks celebrating the Jewish New Year in his home center of Samaria. So welcome back.
Thank you.
And it's a very long title, so I won't read it out. Please begin.
Thank you. Good morning. The talk is about magnetohydrodynamics, which next week you will probably hear a lot about. Magnetohydrodynamics is really what happens when you take two types of classical fields, flow fields and electromagnetic fields, and you combine them together to interact in a single theory. I'm going to talk about this theory and about the group symmetry structures in this theory and about the topological structures that arise in magnetohydrodynamics. Now, when we solve magnetohydrodynamics equations, we are really looking for those 7 functions, which are the magnetic field, the velocity field, and the density field. Of course, B and V are vectors, therefore just a representation of 3 functions put together. Also, there are some derived quantities that are involved. Once you have the magnetic field, you can calculate the current. And once you have the density, you can calculate the pressure through the equation of state. I'm going to assume a barotropic flow, meaning that the pressure only depends on the density and not the temperature. Now, here are the equations. Those are really 7 equations, although if you count 8. But the div B equation is just really a kind of initial condition. Once this is satisfied at time t equals naught, then the equation above it takes care of its satisfaction at all times. Now, what do we have here? Div B equals 0 is just the total magnetic flux going into a closed volume. And if you sum up, you get 0, meaning that what comes in must come out. This equation is really telling you that the magnetic field lines are co-moving. They move with the fluid. And this means that the topology of the field line is conserved. Now, how do you get to this equation? Well, essentially, you start with Ohm laws for a moving media, and you take the limit where J over sigma is null. This means small current density and very high conductivity. So in this case, you get the electric field as a V cross B term. Now you take this, and you take Faraday's law, and you combine together, and you get this equation of MHD. Continuity equation is just the fact that mass is conserved, nothing more. And this equation is Euler equation, which is just Newton's second law for continuous matter, moving under the influence of pressure and magnetic forces, where you have a kind of a Lorentz force over here. Now I'm going to ask 2 questions. Can those equations be derived from a variational principle? And can the numbers of functions describing the problem be reduced? Reduced meaning less than 7. Now, I've worked on those problems and written some papers. One of those is a JFM from 2008. Another is an EPL from 2010. And there are some more newer stuff, which is not yet published in a journal paper, but only in a conference proceeding and in the archive. Let me start by looking at an idea due to Sakurai. Sakurai suggested to look at the magnetic field lines as an intersection of two co-moving surfaces, chi and eta. So this is essentially introducing a coordinate system connected to the magnetic field line. You need a third coordinate. The third coordinate parameterizes the distance along the magnetic field line and was denoted magnetic metage by Lindenberg and myself. Now, if you do that and you choose the surfaces correctly, you get B as grad chi cross grad eta. You can not do it for any topology, so this restricts the topology that I'm going to discuss. Those are also called Euler potentials by some authors. Now, you look at surfaces that are co-moving. This is meaning that the material derivative of chi and eta is null. Now, this is a kind of economy because you have only two equations, and this replaces the 4 equations that you had before, which are those two. Now, let us look at the variational principle, which I am going to suggest, given in terms of this Lagrangian density. The action is, of course, the integral over space and time of the Lagrangian density. The first part of the Lagrangian density contains the kinetic energy terms and 2 potential energy terms. One is due to the internal energy, which is this term over here, and the other is due to the magnetic field energy. The second part of this Lagrangian density contains 4 terms which enforce, by using Lagrange multipliers, the equation of continuity, the existence of 2 co-moving surfaces, and the fact that the magnetic field lines being at the intersection of those 2 surfaces. So it's a trivial matter. If you take a variation with respect to nu, alpha and beta, you get the continuity equations and 2 equations that express the fact that the surfaces chi and eta are co-moving. And of course, when you do the variation with respect to the field, you get this equation, which is just a Sakurai's representation of the magnetic field. If you do a variation with respect to the velocity, you find yourself with this equation, which is reminds the representation by Clebsch, which you get in standard fluid dynamics, but it's more generalized. So it's a kind of a generalized Clebsch representation of the velocity field. And if you do a variation with respect to the density, you get this Bernoulli type of equation, in which W is just the specific enthalpy. Finally, if you do a variation with respect to chi and eta, you get those equations for alpha and beta. Now, what does those variational equations has to do with the physical equations? Well, the fact that the material derivative of chi and eta vanishes is, of course, has to do with replacing those two equations, as I said before. Mass conservation, nothing to be said about that. Now, let's look at the material derivative of V. So you have a set of terms that you have to take the derivative of, and you need to use the equations you got for all those quantities, nu, alpha, beta, chi, and eta. And if you plug everything in, then after a few lines, you get your Euler equation back. Okay? So what we have done, we have succeeded in deriving a variational principle for magnetohydrodynamics of the specific topology assumed. Now, the problem is that you have now, in addition to the original 7 physical variables, you have an additional 5 variables, and that's a total of 12 functions, which is obviously too much for magnetohydrodynamics. Now, how do you get rid of the extra functions? Well, the solution is you rearrange the terms in the Lagrangian. So that's the same Lagrangian as before, but now we dissect it into different sectors. We have this LV and LB, which are only functions of V and B. We have L hat, which is only dependent on the potentials. Now, those terms only give you the generalized Clebsch representation and the Sakurai representation. So what you can do is assume that the velocity and magnetic field are defined by those potentials. So you can just take alpha, beta, nu, chi, and eta once you have them and plug them in the definitions and get the velocity and the magnetic field. So if you take this as a definition, those terms are gone, and you remain with this L hat, which depends on those 6 functions. So the finite Lagrangian contains only 6 functions and yields 6 equations, which are given here. Now, mind you that this is not different from the situation in standard electromagnetic theory. If you want to have a variational principle in standard electromagnetic theory, you have to write the electric and magnetic field in terms of vector and scalar potentials. And then once you have those, you can write the Lagrangian density for the standard electromagnetic theory. So the situation is not different from what we are used to in electromagnetic theory. Okay, what do we have? We have managed to reduce the magnetohydrodynamic equations from 7 equations containing 7 quantities to 6 equations with 6 variables. Furthermore, we have managed to represent magnetohydrodynamics as a variational problems in terms of those 6 variables. A question now is, can we reduce the number of functions even further? And the answer is yes. Let's look at those 2 equations, which tells us that the material derivatives of chi and eta are null. If you write them explicitly and you put for the velocity, you put the a generalized Clebsch representation, then you get those two equations which can be viewed as a set of two equations for the two variables alpha and beta. And of course, they can be trivially solved. And this is the solution. So alpha and beta can be thought of depending on chi, eta, and nu, and you can plug this back into the velocity field and get the expression for the velocity field in terms of chi, eta, and nu. And once you arrange the terms a little bit, it appears in this form, where B here should be viewed as given in terms of the Sakurai representation, meaning grad chi cross grad eta. Now, what we see here is that the velocity field is partitioned naturally into a tangential and normal components with respect to the magnetic field. The normal component depends on chi and eta only, and the tangential part depends on this new function, which really gives only contribution along the magnetic field line. So by construction, if you use this representation of the velocity, those two equations below are satisfied automatically. Now, you can write the Lagrangian density in terms of those four functions, chi, eta, nu, and rho. And after rearranging things, you can have either a compact form in which v and b, of course, depends on the function as we described before, or you can write it explicitly and see what happened now. Yeah. And explicitly in terms of chi, eta, nu, and rho, so you have a four-function field theory of magnetohydrodynamics. Okay, those are the equations, only four equations. And you can conclude that the barotropic magnetohydrodynamics for the topologies assumed is a four-function field theory, which is defined by this Lagrangian. And from this Lagrangian, you can get the equations and boundary of the theory. Now, let's look at the symmetry structure of this Lagrangian. Notice that chi and eta are not defined uniquely. So I can have a new chi and eta, an eta hat and a chi hat, such that the Jacobian is 1, and then you get a symmetry group of the theory, because the Lagrangian does not change under this transformation. Now, if we have a symmetry group, which is a diffeomorphism symmetry group, then we can use the result of this lady, Emma Noether, which tells you that for every continuous symmetry, you have conserved currents. Now, let us look at a small symmetry transformation, meaning that eta hat is eta plus some small change, delta eta, which also a function of chi and eta, and the same for chi. And you put it into this Jacobian equal 1 constraint, and what you get is this equation here below, which is like a divergence equation, div something equals 0 in those eta chi coordinates. And this can be solved easily for any transformation delta f, such that delta eta is a partial derivative of delta f with respect to chi, and delta chi is minus partial derivative of delta eta with respect to delta f. Okay, this is a solution, general solution. Now, if you assume that the equation of motion hold and the boundary condition hold, and you take this variation with respect to those chi and eta, you have the following variational derivative of the Lagrangian, which is, of course, a total time derivative of this quantity. And if you do the same with eta, you have these quantities. And if you add up all the variation, you get these quantities, in which you have both delta chi and delta eta, which are given in terms of the delta f I have shown you before. So plug delta f in, and you get this equation, and take put rho inside in terms of our chi, eta, and mu, and after some manipulation, you get two boundary terms, and this term just here below. So since delta f is arbitrary, we arrive at the following conserved neutral current, which is given here in terms of beta and alpha. Let's summarize. We have shown that MHD has a diffeomorphism symmetry group. We have also found the neutral current connected with this symmetry group. But what is lacking, and this is still research in progress, is the physical interpretation of what those conserved currents really are. Okay. Now let me talk about topology. This part of the talk was initiated some 3 years ago when we had the big party celebrating the 50 years of the Aharonov bomb effect. And it was a conference, and at that time I started to think what connections may be between work in MHD to what Aharonov and Bohm has done in 1959. But it appears that there is a connection, and let me tell you why and how. In Aharonov-Bohm effect, A stands for Aharonov, B for Bohm, but also you can think about A as a source of some electrons that move, and they go around a magnetic flux. The 50 can be thought of 50 Tesla or 50 years to Aharonov-Bohm effect. It goes both ways. Now, the electrons cannot go into the region where there is a magnetic flux. They can go above or below, but the thing is that when they reach the point B, you have some interference pattern, and this is a very unique quantum effect, or is it? Let's look at the magnetic field outside the confined region. There the magnetic field is null, and this means that the vector field is a gradient of some function, but since it's not a simply connected domain, S need not be single valued, and it is not a single valued. You can calculate the magnetic flux using Stokes' theorem. You go from integral B dot ds, and you arrive at this line integral A dot dl. And when you put the grad S in, you see that you just get the discontinuity of this non-single valued function. So this discontinuity has a physical meaning. It's not just something you can brush away.
Excuse me. You put down here that B is equal to 0. So if you have no magnetic field,
That's right.
you have a magnetic flux.
Because the magnetic flux is here, and I'm calculating B over here. Now, when you do this area integral, it must contain the magnetic field, okay? But when you do this line integral, you are integrating in a region where there is no magnetic field, okay? So you have a flux, and this flux must be equal to the discontinuity of S. Is this okay? Yeah?
They fly by the flux, you don't go inside.
Yeah.
Now, the example given in the original paper of Aharonov and Bohm in 1959 is just a round patch of magnetic field, and they calculated the vector potential for it. And if you use this vector potential, it's easy to calculate also this S function. And you get this result, which is, of course, non-single value. Now, what are the main features of the Aharonov-Bohm effect? We have a domain that is not simply connected, but can be made simply connected by introducing a cut. So mathematically speaking, the domain has a non-trivial fundamental homotopy group. The electron, or its wave function, do not feel the magnetic field. So this is a non-local effect, non-locality. The potential vector is a gradient of a non-signal valued function. And of course, gauge freedom is not gone, but you have to be careful just to use a single valued gauges, otherwise you change the physics of the problem.
Asher,
Yeah.
tell us, what is the effect? The fact that the
Okay, let me,
potential is not
maybe I
valued, it's okay.
was not clear enough. You have a source of electrons.
Yeah.
Starting here at point A, you let the electrons go to the other side. They can go either above or below, okay? Now, they don't go into the region of the magnetic field. So they don't feel classically the magnetic field. Nevertheless, you get an interference pattern. Now, this interference has to do with the phase of the electronic wave function. And this phase is really this S over here. This gives you the phase difference, I should say, between those two trajectories. And due to the phase, you see an interference pattern when you put a screen, thank you, over here. Okay? This is something which is well known for 50 years. And It seems, well, people claim it's one of the important points that quantum mechanics has to make about nature.
It's normal diffraction, isn't it? So whatever you put in the middle, the same will happen. What is the significance of this being a flux tube? That's my
Because they don't touch the flux, so why should they care about the flux?
Yeah.
And if you change the flux, you change the magnetic field, which they don't touch, and they don't feel, you still have a change in the interference pattern over here. Okay, let me go to the phase. You see that the phase is dependent on the magnetic flux. So if I change the flux, there would be a different phase difference, and there would be a different interference pattern. Okay?
So it is that the electrons actually feel this vector potential.
Yes.
So it's
Yes.
the non-locality that's so interesting.
Sorry?
It's the non-locality that makes it so interesting.
Yes, because they don't. I mean, there is no Lorentz force on the electron. It can't go inside the region. Okay, but you ask how all this is connected to the first part of the talk, which was about magnetohydrodynamics. Yeah. Well, before I answer this, I want to say something about Bohm's interpretation of quantum mechanics. Now, David Bohm was an adversary of the standard interpretation of quantum mechanics, which is the Copenhagen interpretation. And the thing that bothered David Bohm, I think, is that in quantum mechanics, there is no trajectory for the electron. The electron does not go along some trajectory, but you only look at the observables, and there is a specific mathematical structure that tells you what one should see or should not see. David Bohm was not happy with that, and he said that yes, there are trajectories to the electrons, and there is a velocity field to the electrons, and the velocity field is connected to this S through this gradient. So the phase of the wave function should be interpreted as a potential of the velocity field. But what I will try to suggest is that correspondence can go the other way around. If the velocity field has a potential part, it can be interpreted as maybe a phase of some wave function. But enough quantum mechanics, and let's go back to magnetohydrodynamics. Now, Volger in two papers have suggested two topological constants of motion. One is the magnetic helicity, which is a measure of the degree of knottiness of line of the magnetic field B. And another one is a cross helicity, which has to do with vortex lines and magnetic field lines and the way they are knotted. Now, let us look at the vector potential in terms of the function we introduced before. I mean, the Sakurai representation and chi and eta. In this case, A is just given as chi grad eta plus grad zeta. And if I dot B with A, I get this expression over here because this term falls out. Now, since I have a coordinate system, let me take a piece of chalk and write this down. I can write grad zeta in terms of those coordinates, which is this plus that plus that. Now, when you dot grad chi cross grad eta with grad psi, the first terms cancel out, and what you have is b dot a given in terms of grad zeta with respect to mu times the Jacobian of chi, eta, and mu with respect to x, y, and z. So you have this form. Now plug it into the integral and use the well-known properties of the Jacobian, and you get this expression for the magnetic helicity. Now if you take a single magnetic field line, and you remember that psi and eta are just labels telling you on which magnetic field lines you are, and you look at the integral along this magnetic field line, then you see that unless psi is a non-single valued function, what you will get is absolutely nothing. So zeta is a type of an angle function. It's a non-single valued. It must be discontinuous on some cut, and for the magnetic helicity not to be null. Now, what this shows you is that really you have kind of a, what I would call a magnetic Aharonov-Bohm effect. Well, what is the analogy between magnetic helicity and what we saw in the Aharonov-Bohm effect? Well, you have a domain that is not simply connected, since you have some internal magnetic flux which is knotted inside the external magnetic flux line. Then you have a kind of non-locality, because the external magnetic field line does not touch the internal flux, yet the zeta function is not single valued due to that line. So this is a kind of non-locality. Now, in the potential vector, we have a gradient of a non-single valued function part. It's not entirely a gradient of a non-single valued as in the classical Aharonov-Bohm effect, but you have a part which is a gradient of a non-single valued function. And again, gauge freedom is not gone, but you are only allowed single valued gauges.
This kind of worries me. So your magnetic field you're assuming is the intersection of two surfaces that can be globally smoothly parameterized.
Yeah.
On top of that, you're assuming that your magnetic field is also knotted, right?
Yes.
So making a knotted magnetic field which simultaneously has these pair of surfaces seems a non-trivial task to me.
Well, I will show you how I solve this task in just a few slides. Okay, so really there is, I think, an analogy between what one sees in the MHD and what one sees in quantum mechanics, and it does not have really to do with quantum mechanics, but it has to do with topology. You have a non-trivial topology, and therefore you have those kinds of effects. Now, you can take the discontinuity of zeta and put it into this integral in terms of chi and eta. So essentially what you see is that the magnetic helicity is just the integral of the discontinuity of zeta over the flux. Or you can rephrase it and say that the discontinuity of zeta is just the density of magnetic helicity per unit flux. Now let's look at the cross helicity. Here you have V dot B. Now V is given in terms of the generalized Cleft representation. Let me remind you what this is. It's an alpha grad chi plus a beta grad eta and another function nu over here. And obviously, those, if you dot this with B, the contribution of the two first parts is null, and you remain with grad nu. And then you can write grad nu in terms of chi, eta, and mu. And the same logic that I applied before applies over here. And what you have is a V dot B, which is a grad, a partial derivative of nu with respect to mu, times this Jacobian with respect to chi, eta, and mu. And you can plug this inside the cross helicity integral, and you get this form. Now, tricks goes the same as before. You look at a single magnetic field line, and you see that unless nu is non-single valued, then you would not have any contribution to the cross helicity. So it must be a non-single valued function to have a non-trivial cross helicity. And you can write the cross helicity as an integral of the discontinuity of nu d phi. Well, d phi is just the magnetic flux. So again, you can talk about a cross Aharonov-Bohm effect. And the similarities are as follows. You have a non-simply connected domain. And this is due to the fact that the magnetic field line is noted inside an external vortex line. The external vortex line does not touch the internal flux. Yes, the nu function is not single valued due to that line. So this is a kind of a topological non-locality. And the velocity field has a gradient of a non-single valued function part. And this part can be interpreted as a phase according to Bohm's casual interpretation correspondence. Now, again, you can rephrase and say that the discontinuity of nu is the density of a cross helicity per unit flux. But now there is a twist to it, because remember that nu is one of our variational variables, and zeta is just an auxiliary function. And we have an equation for it. We got a variational equation for nu, which says that the material derivative of nu is half v squared minus the enthalpy, the specific enthalpy. But look at those sides. The right side of the equation is obviously single-valued, because V is a single-valued function. It's a physical function, and so is the enthalpy. So what does this mean? It means that the left-hand side might be single-valued as well. And this means that the material derivative of delta nu must be null. So not only the cross helicity is conserved, but also the cross helicity per unit flux is conserved as well. So this is like a new conservation law of MHD. Let me conclude. That's not really a conclusion, because I'm going to show an analytical example after that. But let's summarize. It is shown that there are two inherent Aharonov-Bohm effects in MHD. In each case, a magnetic flux induces a phase, with a parenthesis, on quantities that do not come under the influence of the magnetic field directly. Those quantities include the velocity fields and external magnetic field. And again, external is in parentheses. Two phases quantify two well-known topological conservation law of the magnetic and cross helicity. One of those phases is useful for introducing a very efficient variational principle for MHD, which is given in terms of only 4 independent functions for non-stationary flows of the appropriate topology. And of course, this is less than the 7 variables which appears in the standard equation of MHD. Now, the real conclusion is by giving just an analytical example to show you how all those quantities can be really calculated. And for this, I've used the help of Keith's paper here from 1969. But I think in your paper, it's U and omega and not A and B. So it's a bit different, but not too different. We have this representation of A in terms of standard cylindrical coordinates. And we have a B, which is a curl of this A, and this big D is defined over here. Now, the function psi introduced in the 1969 paper is such that grad psi dot A and grad psi dot B are both null. But now I'm going to do something else. I'm going to introduce a new variable, which is a small r. Now, this small r is really a radius of a torus, which is in the r equal 1. It's centered about a line, a circle with r equal 1 and z equals 0. And you have, I assume that psi is a function of r. So you have surfaces of constant psi which are nested tori. Now, I've drawn one of those magnetic field lines, and I assume some specific psi, and the psi I assume is r plus r to the 3, but you can take anything you like almost, and took alpha equal 1, and you just see that everything is just knotted on those tori. You just plot 20 rotations over here, otherwise it gets messy. Now, in addition to this r, which just tells you in what tori you are, I need coordinates on the tori, and those are two angles. The short way angle which I call eta star, and the long way angle which I call phi star. Now, you can calculate chi and eta in terms of those functions. And chi is just psi, really, up to some alpha. And eta is phi, the azimuthal angle, plus some function of z and r, which I calculated in terms of small r, the radius of the tori, and the short wave angle eta star. So you can see what C is, and you can see that you can calculate them in terms of two analytic functions, which are I and double I, are given just here below. And those are non-single valued functions. I drawn them for some value of R, and you can see that after you complete a full circle from 0 to 2 pi, you do not get back to the same place. Now, what we need in order to calculate the helicity is this zeta, and this zeta was calculated, and the discontinuity of zeta was calculated. And when you plug everything into the magnetic helicity, you get this result, which you can also get by direct calculation using A and B and just plugging it in. So this all machinery works out, and you can get the correct value of the magnetic helicity. And by this slide, I conclude my talk, and I thank you very much for listening.
Very good. Any comments, questions?
In your last example, so it seems to me it's essential that you make a choice so you have rational wrappings on those. Because if the slope is irrational, it can't be the intersection of two levels, two sets. Right? So some choice must be made that the magnetic field lines, when they travel around, come back to themselves.
Why should they come back to themselves? They never. It's a ergodic filling of the surface.
So if you have such a flow on a torus, things are coming back to themselves infinitely often, right? And then if there's a level set of some surface, pair of surfaces, it's going to be completely insane. It just can't work, right?
No. Let me explain. First, the magnetic field lines are are only allowed to be on the torus. So the one surface is given. That's the torus.
Yeah.
And the second, let me show you the.
Is each field line? Are you thinking of each field line as being the intersection of two surfaces?
It is. Let me show you why. The first is just the tori, so it's alpha psi.
I can't think in terms of formula. Sorry. What are the two surfaces? One is a torus.
Yes.
And what's the other surface?
It's given by the constant value of phi plus this C function. So it's doubly non-single valued. It's non-single valued in the phi direction, and it's non-single valued in the eta direction.
But the level sets of this function build up on themselves everywhere. Right? So
Okay.
you can't have a function whose values build up on each other without being a constant function. Right? I mean, you can't, if you define a continuous function on a dense set, it has to be constant. We can talk about this later. I don't mean to monopolize.
And this is
you have to have a rational.
This is a closed mathematical solution. You can just follow the mathematics and see that you get this equation. Now, I admit it would be difficult to draw such a thing, but well, that's the way it is.
But that surface Yeah, if you took a local bit of it and went round and round the torus, it would become infinitely stacked on itself.
Mm-hmm.
Right, I mean, you can
That's
choose the
horrible
torus,
as a
but if you have
surface.
irrational wrapping in the torus.
Yeah, but it doesn't work.
Have to be
Okay.
traversed. It's just restricted to the torus. The value of that function is specified on the dense set on the torus. Well, listen, can I talk topology for a second? Let's fix the torus. Your second function's value is constant along field lines on that torus, correct?
Field lines are on levels of constant
Yeah,
values.
so you have one is the torus, and the other is another function which is constant on field lines on the torus. Correct? That's your second function.
Yeah.
So those field lines have irrational slope. They are dense.
Yeah.
Therefore, your function is constant on a dense set, and a continuous function that's constant on a dense set is constant everywhere. So therefore, your second function is constant on the torus.
Yeah.
But
Function of R only.
it's not constant. You can just plug numbers in it and see that it's not constant.
Then there's a contradiction that has to be resolved.
Right. I could try to think about your function, but the topology seems quite compelling.
Yeah.
I mean, if it's rational, I mean, clearly if you make a choice, then basically it's a Hopf vibration, and then everything's cool. I don't have a problem with that. It's just something that needs a little more care. So, to make this a globally continuous function. It's
Well,
not
we
constant.
can just take Mathematica and draw it, and you can see how the
Yeah, should do that.
Yeah,
The-
that'd be the thing to do. Yeah, you've stopped one slide too soon. We need to see slide number 80 with the picture.
this one.
No, 80.
I mean, a Hopf vibration is fine.
Direction.
I see. Oh, no, I'm sorry. I thought that was your
Especially
last
if
slide.
it's
You want this one?
I want a new slide that you haven't done yet.
Ah, okay. I can do that later.
No, that's a key question, I think.
Well, I mean, I don't think it really matters, because if you pick it so they're rational. Rational.
But the thing is, they are, as r, little r varies continuously, I think you go through every possible winding number.
Well, if you go through possible, if it's not the Hopf vibration, if it varies on the tori, then trouble's hidden.
I think it varies from one to, is that not right? Your winding number.
It may, but it doesn't have to.
It doesn't have to.
Yeah, but if
perhaps.
you cook it so it doesn't, then you have a Hopf vibration, then it's okay.
Yeah, then
we had to
maybe.
talk about this before, maybe. Okay.
What you have is a discontinuity of zeta, which just changes between one r and
Continuously.
another. Yeah.
Does it change continuously as a function of r, little r?
Yeah.
Well, good point. Any other questions? I think all this does look very powerful. There are these, I think the example is important to try and really see what it all means. But the relationship with helicity and cross-helicity is, of course, very interesting. And the link with the Aharonov-Bohm effect is new and interesting. So, wonderful. Thank you very much.